Good morning to all. Today we are going to discuss about the electron probability density. My name is Anixis Mandhu and I am from 3rd year integrated MSc Physics, Marine College, Kuttikana. So let's delve into our topic. In Bohr's model of the hydrogen atom, the electron is visualized as revolving around the nucleus in a circular path. This model is pictured in a spherical polar coordinate system, and it implies that if a suitable experiment were performed, the electron would always be found in a distance of r is equal to n square a0, where n is the quantum number of the orbit and a0 is the radius of the innermost orbit, and it is also called Bohr radius. So the electron is n square a0 distant away from the nucleus, and it is in the equatorial plane theta is equal to 90 degree, while its azimuth angle phi always changes with time. The quantum theory of the hydrogen atom modifies the Bohr model in two ways. First one, no definite value of r, theta or phi can be given, but only the relative probabilities for finding the electron at various locations. This imprecision is a consequence of the wave nature of electron. Second is that we cannot even think of the electron as moving around the nucleus in conventional sense, since the probability density phi square is independent of time and varies from place to place. The probability density phi square that corresponds to the electron wave function phi is equal to r theta phi in hydrogen atom is phi square is equal to r square theta square phi square. As usual, the square of any function that is complex to be replaced by the product of the function and its complex conjugate. We see that the azimuthal wave function is given by phi of phi is equal to a e raised to I ml phi. The azimuthal probability density phi square is therefore phi square is equal to phi star phi is equal to a square e raised to minus I ml phi e raised to I ml phi is equal to a square e raised to 0, that is equal to a square. The likelihood of finding electron at a particular azimuthal angle phi in a constant that does not depend upon phi at all. The electron's probability density is symmetrical about the z-axis regardless of the quantum state it is in, and the electron has the same chance of being found at one angle phi as at another. The radial part r of the wave function, in contrast with phi, not only varies with r but does so in a different way for each combination of quantum numbers n and l. Now let's see the behavior of r of r. For a state, the radial wave function r of r is maximum at the nucleus, that is r is equal to 0, r is equal to 0. This indicates that there is a high probability of finding the electron at nucleus for these states. In contrast, for states with angular momentum p, d, etc., the value of r of r is 0 at r is equal to 0, that is equal to 0. This reflects the nature of these states where the electron cannot be found at the nucleus due to its angular momentum. So the figure shows the variation with distance from the nucleus of the radial part of the electron wave function in hydrogen for various quantum states. The quantity a0 is equal to 0.053 in the radius of the first Bohr orbit. So we can say see that in the graph shows the probability of finding electron in different states. The first one shows 1s, and the second one shows 1s, 2s and 2p. The third one shows 3s, 3p and 3d. We can see that the probability of finding the electron changes with the state. So now let's summarize what we have learned. The probability of finding that electron in the azimuth angle is a constant, that it does not depend on the phi at all, and the radial part r of the wave function, in contrast to phi, not only varies with r but also does in a different way for each combination of quantum numbers n and l, and the value of probability always changes with radial part r in different combinations in different way. So that is the probability density of electron. Thank you.